Good afternoon. As Janice said, I'm Richard Turton. I'm a professor of chemical engineering at West Virginia University. And in, I guess, John Cleese's famous words, now for something completely different. So this is going to be a little bit different from something that you've probably seen previously in this conference. I looked at the program, and I think I'm one of only 5 university professors here, and as far as I could figure out, I'm probably the only one who's actually teaching undergraduates. So I'm a rare person at this particular venue, at least. So what I hope to do is talk to you a little bit about a sort of paradigm in education that's occurring right now because of some of the many issues involved with the sort of tech-savvy newer generation. And then for the second half of the talk, I'm going to explain a little bit about how we've tried to address this problem at West Virginia University through an operated training system and an immersive training system that I was privileged to be a part of developing and implementing. Before I get going, I should give you a little bit of background on myself. As I say, I'm a professor at West Virginia University. From my accent, you can probably tell I'm not a native West Virginian. I'm originally from England. I went to the University of Nottingham, and coming back to something that Janice said about her daughter going to RPI and being impressed by the architecture and all the boys there, right? Well, it turns out that Nottingham, I know for those of you who may or may not know this, but Nottingham was a big centre for industrial production during World War II. And of course, at that time, all the men were of eligible age were off fighting the war, and a lot of the factories got basically manned by young women who were brought in from all over the place. And at one point, the ratio of men to women in Nottingham was something like 5 to 1, okay? So this was true in World War II. Of course, that wasn't true afterwards, but it's amazing how that statistic, or the myth of that statistic, basically perpetuated through the 1960s and 1970s. So I have to say that one of the reasons that I went to Nottingham rather than Imperial College or Birmingham was some of the other options was that I was very impressed with all the ratio of women to men. So, and I think I turned out okay. So it wasn't such a bad decision. Anyway, a little bit of background on West Virginia University. It's a land-grant university, has approximately 32,000 students spread over 3 main campuses. The major one is in Morgantown, with satellite campuses in Kaiser, West Virginia, and Montgomery, West Virginia. It's has all the full complement of academic programs. So it has a law school, has a medical school, has creative arts center, has a full athletic program, it has engineering, it has sciences, humanities, everything. And it's one of, I think, about 22 full complemented or fully complemented academic programs that are land-grant universities in the country. Chemical engineering program has approximately 200 students between the sophomore and junior years. It's typically split by sort of 80, 60, 60, 60 in the senior and 80 in the sophomore year. That number has grown quite a lot in the last few years, and if you look around the country, the number of chemical engineering students has gone up quite a lot, probably doubled in the last 4 or 5 years. Not clear why that is the case, but obviously the improving energy situation has a lot to do with that. Our curriculum is traditional chemical engineering, material energy balances, heat transfer, fluid dynamics, thermodynamics, reaction engineering, separations, control, senior design unit operations lab. I'm not quite sure why I've capitalized thermodynamics. Maybe that's some sort of Freudian slip, but I'm not putting it in any more important or less important than the other topics. So it's a fairly traditional chemical engineering program. Okay. So there's an education paradigm, or the education paradigm is changing significantly. And basically, what we're seeing is that students now learn very differently from the way that they learned 20 years ago or even 10 years ago. I put this quote up because it's one I love, although you'll think I'm cruel and unreasonable, but it's true, I think, at least in terms of the way the older generation always perceives the younger generation. So I'm going to read it. The children now love luxury. They have bad manners, contempt for authority. They show disrespect for elders and love chatter in the place of exercise. Okay? So this, I remember quite vividly my father saying these sort of things to me when I was growing up. And in Mark Twain's words, it's amazing as you get older how much smarter your father gets. So I find myself having similar thoughts about this. Interestingly, it's a quote that is sometimes attributed to Socrates. It's not quite true. I think it's actually from this fellow Kenneth Freeman. It's based on a dissertation from Cambridge in 1907. And what he did was he was going back and looking at all the ancients and their sort of views that the older generation had towards the younger generation. So this is a sort of simplified version of what he found in a lot of texts. Okay, so So despite this age-old complaint that the older generation have about the young, which is probably not true, but some people think that there's a lot of truth in it, what we do find now, at least what I do find now, is that the learning methods are changing, that the type of student that's coming into the engineering program is significantly different from the person who came in 10, 15 and 20 years ago, because their life experience is so different from the student that was basically coming in at that time. Okay. Okay, so research conducted over the past few decades shows that it's impossible for students to take in and process all the information that's presented during a typical lecture, and that's typically 50 minutes, okay? And yet this is one of the primary ways college students are taught, particularly in introductory courses. So you can see that that's a big problem, right? 30 years ago, I don't think, maybe I was so enthusiastic I didn't worry too much whether the students were getting it or not. I was wrapped up in my own enthusiasm. But certainly in the last few years, I've started to see that if you do a sort of traditional lecture with PowerPoint slides, after about 15 minutes, you've lost pretty much all the students in the class. And you know, there are ways to deal with this, sort of active learning procedures where you stop and you ask for discussions, etc., etc. But this becomes much more important now than it was, say, I think 10 years ago. Things that I try to remind myself about students coming up, or high school students, some of these things. I'm not going to go through all the list of them, but I'm sure some of them sort of are interesting. I mean, most of these kids have grown up and never known what a search engine, or never known not what a search engine is. They've lived in a world that has always had DVDs. They probably don't know what the Dewey Decimal System is, let alone understand it, although I'm not sure anybody actually understands the Dewey Decimal System. They've lived without they've never sort of lived without text messaging or iPads, iPods, or Google or anything like this. So it's certainly, compared to me when I was growing up, I had none of these things. And for me, and I think people of my generation, having seen this trend and this change, to me it's quite remarkable. You know, things that I used to do in school by hand is now, that would take me a day, it's almost a click of a button. And when you've had that, you have an appreciation for what's involved in that. I think when you don't have that, you lose that appreciation. And there's some good things about that, but there's some bad things as well. So here's another set of interesting facts, I think. So looking on the right there, this is from a New York Times article. So they did basically a survey which was based on a couple of studies, one by the Pew Interest in American Life Project and the other by the Common Sense Media. Both of those are pretty reputable sources. They surveyed about 3,000 teachers. And even though the results of this are somewhat subjective in the sense that it's difficult to quantify this, because there's so many results that so many teachers have sort of come up with similar sort of conclusions, that they feel that the conclusions from these studies are pretty true and relevant. So, as it points out, it all comes down to attention span. In both surveys, teachers expressed concern that students used to fast-paced, always changing activities are less able to focus on academic tasks for a long period of time or prolonged period of time. Many teachers feel that they must change the way they teach to ensure that the students concentrate enough to learn. Most teachers seem to feel that children learn differently. However, they are of differing opinions about how much technology can be used to address the problem. So this, what I'm trying to point out here is this is a real problem. This is not a perceived problem from a professor who students might consider to be a dinosaur and just not changing with the times. Is that things have changed, and the question is, how do we change our learning techniques to engage these students and make sure that they actually are able to understand these concepts that are very important in engineering, do not only to understand them, but to be challenged by them, and also to really understand them and not just sort of deal with them on a superficial level. Okay. Another interesting sort of fact on the right-hand side here is this: students spend more time each year online browsing the internet, and it sort of shows, you know, for social networks is about 80%, Wikipedia 100%, books in libraries 10%. Okay, so when I was a student, okay, obviously I didn't spend any time on the internet because the internet didn't exist, and I spent a lot of time in the library. When I was, you know, even up until 10 or 15 years ago, if something was not written in a book or in a peer-reviewed journal, the general feeling in academia was that it did not exist or it was not worth considering. That has flipped completely now, what with Wikipedia and all that other information. Doesn't mean to say that everything on the internet is correct, but certainly it's a go-to first place for pretty much everybody I know to go and look for information. So again, that's a huge paradigm shift that we've adjusted to, but there are also some sort of issues with that. But anyway, what I'm trying to put forward here is there is a paradigm shift in the way students learn and the way we teach. So one solution to this is this term called flipping the classroom. I don't know if anybody is familiar with this. It's a sort of buzzword that's used in education. And it's sort of been presented in a couple of high-profile publications. In essence, what you do is you don't use the classroom to teach material. What you do is you pre-record your material, say, on a video. This might be just doing PowerPoint slides, you talking, explaining things, and then you make that information available to the students. The students can then pull that off the internet. They can look at it a number of times. And you expect them to learn this material, or at least look through it. And then when they do come to class, you don't spend time talking about this, you assume they've done this, and then you go to this sort of higher level function where you're simulating that knowledge, either through problem solving, which is typical for engineering. You'll set them problems. So they come in and do the homework in the class, and they're doing the sort of classwork, if you like, at home. So that's the flipping part of it. And you can do discussions and debates for classes that will warrant that. Is this successful? Yes or no? Again, it depends on the student. If you have a motivated student that's going to actually listen to the material, make sure they know it before they come to class, it can be very effective. If you've got a student that wants to be told everything and doesn't really want to do that, then I think it's probably a bad way, because what happens is they get behind very quickly and it's difficult for them to catch up. But this is a paradigm that's actively being used both at universities and to a certain extent in high schools. Okay, so let me take let me go forward now and talk about the operator training system and just take an example here. This is the senior design course that I teach at WVU. It's a traditional course. I've color-coded things here. So red is lecture series with problem assignments. Green will be some in-class exercises, blue will be discussions, and this purple will be a project outside the class. So as you can see, I start off with process diagrams, PFDs and stuff like that. I talk about the structure of the process flow diagram, do some in-class exercises. I talk about batch processing. I review the design and performance of existing equipment, so there'll be in-class exercises, homeworks, and lectures on that. Engineering economics, time value of money, cost of manufacturing, profitability analysis, etc. So again, some in-class exercises. Optimization, heat exchange networks, there's also some in-class exercises here. Ethics and safety, we have modules on, often involving discussions, case studies, and things like this. And then there'll be at least one project which is outside the class. Okay? So this is a fairly sort of traditional, in some ways two-dimensional way of presenting information. I try to make my PowerPoints interesting, I try to make the lectures interesting, I try to engage the students, we will break things up, etc., etc. But it's pretty much people sitting there, me talking, and the interaction is this way there, and there's a little bit of group interaction and talking among each other and working out problems, but it's still very much a sort of classroom atmosphere. So that's what we've been doing. So if I talk about one aspect of that, you know, like process flow diagrams, P&IDs, control loops, they'll do some little bit of work in class, they'll do some homework set assignments, and then they will take some, you know, there'll probably be a problem or two on the exam. And the way we assess whether we've done a good job is how they do in the homeworks and the exams. And they seem to do okay, but there's only so much you can sort of really ask them in an exam. So you always worry about, do they really get it? Okay? So my hypothesis is that if you can experience a process through an operated training system and an immersive training system, it gives you a completely different and deeper experience of that particular aspect, in this case P&IDs and process flow diagrams. And I think because of that, it's an experience that will stay with you for a much longer period of time than just having this sort of given to you in a lecture by a professor. So let's talk about what the facilities we have at West Virginia University and how we sort of utilize them. So here is a diagram of the setup that we have in our lab. These are the instructor stations in which the dynamic model, which is run on DynSim, the Schneider Electric DynSim, that's running on the background. This plant is an integrated gasification combined cycle power plant. It has 20 individual process units. Pretty much all of them are modeled rigorously. It's a real-time simulation distributed on 16 CPUs that's capable of running at about 180% of real time, 100 to 180%, so it can run at real time. There's a historian that basically updates the HMIs on these control consoles here, shown here and here. So basically the information on the HMIs is basically updated via the dynamic model every second. So essentially you're simulating a IGCC power plant as closely as one can do within this environment. Not shown in this diagram, but in a room next door, somewhere here, I guess, in scale, there is a immersive training system that basically has a virtual model of all 22 process units in the plant. And students can basically have, through a gamepad, can manipulate an avatar through the plant and do a variety of things with the equipment there. The ITS and the OTS are linked together. So if I'm out in the virtual world and I turn a pump on, that pump will basically show up here. It will show up on the OTS as being flipped and turned on. And the model will deal with that. You know, liquid will flow out of that. Likewise, if I close a valve, maybe an inlet valve to a tank, then that will also change in the OTS. That might cause the low alarm to be triggered in a drum, which might cause a pump to cavitate or switch off through whatever digital logic is there. So they are connected in this sense. So what happens in one is reflected in the other side. Okay. So here's an example maybe of what you can do with these types of tools in a design class. So on the left-hand side is a static P&ID. So I might take this and I might go and sort of point things out and ask a student, say, okay, well, I've got a PI here, what is that? And, you know, they're all looking down, hoping that it's not going to be them that ask. Then finally I pick on somebody and somebody will mutter, well, maybe it's a pressure indicator. And I say, fine. Is it situated in the control room or not? And then they have to look in the book and see what sort of the configuration is and if it's in the control room or not, depending on the symbol that's used. And you can do that, and you can see that that's an interesting exercise, but it's probably not going to stick with them very much. Or you can stick them in front of this screen here, which is essentially the HMI representation of that P&ID. And they can, first of all, you can see it in color. Two, you can see green and red valves indicating off and on or open and closed. Likewise, the pumps, you can see red being on, green being off, etc. All the tags with white numbers in them are essentially controllers, so the student can click on that, they can look at what's going on, they can change it from auto to manual, they can reset a set point, they can actually investigate what happens in the plant to do this. So it's a far more interactive and I think a better learning environment for students. Likewise, they can do sort of controlled experiments. So here's an example where, here we have some slurry tanks which are basically making up a coal slurry for the gasifier. And what we've done here is we put an increase in the slurry flow rate out of one of these tanks. Here's the gasifier, so basically you can check to see what happens in the gasifier. Essentially what's going to happen is you're putting more coal in, the controls will drag the oxygen level up to make sure that the stoichiometry is met, or the desired stoichiometry is met. And what you'll see is because there is now more energy being released, there's more steam that's going to be produced here, therefore the pressure in this drum will start to increase. And then some other controls will start to come in. The valve on the outlet of that drum will start to open to let more steam out. If that is not, if that doesn't allow enough steam out, then there's a safety relief valve that will start to open to release the pressure, and it will finally bring the controlled pressure back down to where you want it. So this is a very interactive way for students to learn intuitively about control systems. I contrast that with a setup that you might see in a traditional control course where perhaps the most complicated sort of setup that you'll get in the introductory control course will be two stirred tanks hooked together, and you'll write out the equations for this and you'll Laplace transform them and do some sort of Bode plot on them or a Nyquist stability test and look at that. But to me, this is a very dry, again, two-dimensional way of learning about control. Actually being able to play with the plant and look at this is a far more a rich environment and really a much better learning tool to do this. On the 3D side, the immersive training simulator, we just got some features here. So the students can basically operate an avatar with a gamepad. They can turn valves. They can turn on pumps. They can look at trends for any number of different process variables. They can do this augmented reality where they can go in and they can open up the wall of a column and look inside and see what's going on. This is very important when you're teaching these types of courses, because at least nowadays, and I suspect it's always been the case, but certainly nowadays, if you give a student a 2D drawing of something, I think most students do not understand what that is. It's really a 2D drawing. They do not get the full depth of what is happening inside a column or a heat exchanger. When they see something in 3D, you get much better appreciation of it. So just in terms of exposing them to what's going on inside this equipment, this is a fantastic tool. And likewise, you can look at things like gas leaks and stuff like this and sort of talk about safety training. Plant familiarization and walkthroughs, I'll talk a little bit about that, and then the integration of control room with field personnel, so you could actually have a startup scenario. We could have somebody in the control room trying to start the plant up, and they find out that a valve's closed in the plant, so they send a field operator out, i.e. somebody in the immersive training piece, to actually go and open the valve. They can confirm that that valve is open, they can see it on the HMI, and they can move forward through the startup, so they can actually coordinate scenarios where students can work together on this. So here's an example. This is part of the I think this is the sour gas unit at the IGCC. I'm always impressed when I see this, the quality of the graphics. They really are superb. This actually doesn't give it, I don't think, credit. The iSim engine that Schneider Electric uses is really superb, and they have this this technique to sort of overlay photorealistic images on terms of these CAD drawings. And you really, when you're operating that avatar, you really do feel like you're in a plant. Here are some of the augmented reality. So here we have two bundles sitting in a shell of fluid. Here we have the overflow weir for a reboiler, and here you can see some idea. This is a tray column, and then there's a pack section up here. So again, taking the students in for these sort of junior level classes where you start talking about this sort of equipment, being able to pull this off and actually get them to have a look inside the equipment is much better than sort of any 2D drawing in a book. They really sort of get a much better, improved idea of what's going on here. Safety training, we haven't done this, but certainly there's all sorts of ways that you can think about doing safety training. You know, you put an avatar there and you say, okay, you can see this fire, what do? You know, you've got to figure out, you know, on the P&ID, what's the valve that I can close to turn the fuel that's basically pushing that fire on there, or what's the sequence that I need to do to actually get this problem out. If this is a poisonous gas, you know, you have the option of actually changing the equipment that the avatar has on, so you may need full breathing apparatus and stuff like this. So there's all sorts of scenarios that you can play like that. So I'm getting close to the end here, so let me wrap it up. What we've done is we've been able to successfully implement the OTS and ITS in a variety of courses. We use it in the freshman introduction. This is our kind of plug to get students into chemical engineering, certainly showing them this, being, you know, sort of handing them over the avatar and you know, allowing them to wander through the plant using the avatar is a big draw for freshman students. We use it in fluids and heat transfers to sort of illustrate different types of equipment. We can show a pump cavitating, for example. You actually hear the cavitation. We talked about you know, sound being in a sort of extra dimension. There's no smell yet. That's probably just as well if it's there's a lot of hydrogen sulfide floating around here, so we're probably better off just keeping that out for the moment. The design course we've used extensively in the design course. The control course as well, so we've actually looked at open loop responses, closed loop responses, looked at different control schemes, and this is doing it on the OTS is a really nice way of doing it. And then I currently have a student who's sort of coming up and thinking about setting design modules that will allow self-guided instruction. So one is a tour through the process. Another one is looking at instrument and control I/O lists. So actually sort of go through and check a line on a P&ID and check that all the instrumentation is there. We have talked about tutorial for plant layout and equipment arrangement. So, you know, why are the pumps sitting on the ground? Why are the control valves on the ground? Why is the bottom of the column 15 feet above the floor and not resting on the column like everybody thinks it is, or at least all the students think it is. So you can sort of actually sort of have a talk through that and explain those things. And then there's all the sort of process changes. So in conclusion, my feeling is that this is a really wonderful tool. I think it's going to be used more and more in undergraduate education. And to me, it's, I was very privileged to sort of be a part of the team that sort of built this and was able to implement it at the university. So finally, I'd like to acknowledge my colleagues at West Virginia University, Steve Zitney, who is the project manager at NETL, and also Department of Energy for funding the original work. And there should be a thanks to Schneider there. I guess you got an older version, but also I'd like to thank Schneider Electric, formerly Invensis, for really doing a lot of the work and their continued support. So with that, I'd like to call a halt, and I guess we're going to start the panel discussion. Is that right? Okay. Thank you.